So I am Ashrik and I am from Group 14. We are given with set 2. So let's start the question 1. So here's the question. An industrial monitoring system fails its safety checks because the calibration module expects sensor reading in IEEE 754 format, but the conversion circuit has malfunctioned. There are two critical values: minus 85.125, its absolute temperature, and 5 by 6, its pressure coefficient, to their correct IEEE 754 single precision hexadecimal representation to complete the calibration process. So we need to convert each value into IEEE 754 single precision hexadecimal format to restore the safety monitoring. So let us try to solve the question. So what's the scenario in the question is an industrial monitoring system is given. It is a failed because there is some problem in safety checks. Now, what are the values given? Minus 85.125, it's the absolute zero temperature, and the 5 by 6, it's a pressure coefficient. So what we should do, the task is we should manually convert the two numbers into IEEE 754 format with our own knowledge. So the final goal is we need to write the 32-bit hexadecimal representation in IEEE 754 single precision format. So let us just quickly give, I'll give you a crisp of IEEE 754 format. So the first bit in the IEEE 754 format is the sign bit. So the sign bit is 0 when it is positive number, and 1 it is negative when it is negative number. So the exponent are the next 8 bits. It doesn't contain the actual exponent of the number, but it is the biased exponent. So how to find actual exponent is we should find the biased exponent, and then we should subtract 127 to that to get the actual exponent. So the biased exponent is directly the 8 bits converted into the number, the 10 decimal number, and then the next 23 bits are the mantissa. It is also called as the fractional part, and the number which is after the decimal, like some 0.5 or 0.32, the it is the mantissa part. So the mantissa is calculated by normal binary representation, binary conversion. Okay, so with this, let's start the first one. So we should convert minus 85.125 into IEEE 754 format. So the first the first bit is sign. So let us check the sign of the number. The number sign is negative, so the first bit is 1. So the first bit is 1, and then now let us go to the integer part. The integer part in the number is the 85.125 as integer 85. So we need to convert 85 into the binary number. Binary number is found by dividing 2 and then taking the reminders and summing up and the padding all the reminders will give us a final binary representation of some number, some integer number. So we do that. 85 divided by 2 gives us 42 and the remainder 1. So now now we divide 42 again by 2, so we get 21 and remainder 0. And then now 21 is divided by 2, it gives 10 and remainder 1. So now it is divided again with 2, 10 is divided again with 2, it gives 5 and remainder 0. So 5 is divided by 2 and it is given 2, remainder 1. So now 2 is divided by 2, it gives 1, remainder 0. And when 1 is divided by 2, and then it is given, it gives us 0, remainder 1. So we should read the reminders from bottom to top. So now what we do is 0. What is the first number is 0, and read the reading reminders from bottom to top. So we get 1. The last reminder is 1. So and then it's 0, it's 1, it's 0, it's 1, and then 0 and then 1. So the final number is 1010101. So converting 85 into binary number gives us 1010101. And now let's go into the fractional part. The fractional part here in the number minus 85.125 is absolutely 0.125. So let's try to convert 0.125 into binary number. This is a bit different to what we do in the integer part, converting into binary format. So here in the fractional part, we multiply with 2 because it is 2 power minus 1, 2 power minus 2, 2 power minus 3, and so on. So here we multiply with 2, and then we take the we take the integer part of the number of the result. So 0.125 is multiplied by 2, and then it gives 0.25. So its integer part is 0, and then 0.25 multiplied by 2, it gives 0.5, and then the number is its integer part is 0, and then 0.5 multiplied by 2 gives us 1, so it gives us 1. So the final number is 0.001. It is like just calculating 2 power minus 1 and 2 power minus 2, 2 power minus 3. It's the same way, but a kind of logical way of solving fractional parts. So let's now just normalize the fractional part mantissa. So in order to get into IEEE 754 format, so in the IEEE 754 format, the first bit is always a 1, always 1 in converting it to not we are normalizing the number. So we should get into the form 1 point fraction and then 2 power exponent. So what we got is 1010101. It is the integer part, and then the mantissa fraction is 0.001. So this is the final number 1010101.001. So we need to get into the form of 1 point fraction and 2 power exponent. So when we convert this, we move by 6. We move the decimal by 6 times. So we get it 1.010101001 into 2 power 6. So this is a normalized form. We should basically get 1 at the start and then some decimal into some 2 power exponent. Okay, let's we have already discussed about the biased exponent. So what we got, the exponent here is 6. So this is the actual exponent. So we need to get the biased exponent. So we add 127. When we are converting from IEEE 754 to normal, we subtract by 127. Now in the reverse manner, we add 127. So we get 133. 133 is converted to binary number in the similar fashion of 85. Like we divide by 2 and then check the remainder. We divide by, again the divisor is divided by 2, and then it is check the remainder, and then we get 1000101. It is very clear here up to here. So now let's try to solve the mantissa part. So from normalized form, fractional part is 0, 1, 0, 0, 1001. So we can just see it in the above 4th point. Just the mantissa is the 8-bit number. So we should add some zeros to get it 23-bit. So we are padding some zeros until we get 23 bits. So it becomes 0, 1, 0, 1, 0, 1, 0, 0, 1, and some number of zeros to get 23 bits. So we finally assemble all the 32 bits. So the first one is the sign bit, and then 1, which one, and then we now write the integer part 1010101, and then after the integer part, after 1 sign bit, we write exponent. Exponent is 100000101. So we should actually write the exponent after 1, and then now we write the mantissa part 010101001, and then zeros up till we get 23 bits, and then now we convert it to hexadecimal format. So what we do is we group into 4 bits. So we get some 1 plus 8 plus 13 is like something like 9 plus 32 bits. So we get 8 groups, each containing 4 bits. So the first 4 bits is 1100. So 1100 is basically 1, 2, so 1, 2, 4, and 8, 12. So 12 gives us C, as A gives us 10, B gives us 11, C is 12. So we write plus C, and then 0010 is 2, and then 1010 is again 8 plus 2, it's 10, and then 1010 is again a, 0100 is again 4, is 4 again, and then now we get 0000, and then remaining are zeros. So what we get is 0x. 0x is very like we should put it every time when we are representing it in the hexadecimal format in order to in order to get the feel of hexadecimal format, in order to identify or recognize the hexadecimal format, we need to put the 0x for every kind of representation in hexadecimal. So now we get the first one is C, so C, and then 2 A and 400. So this is the final number. So the final number is 0xC2AA400. So now I'll give chance to Ramana to continue the next one.
Myself, P. Ramana. We will do same thing for 5 by 6 fraction. We will try to convert this into IEEE 754 single precision format. There are 5 parts: sign bit, fractional mantissa, biased exponent, assemble, group, and convert to hexadecimal format. For sign bit, since 5 by 6 is positive, we will assign s equals to 0. Next come to second part, fractional mantissa. Write 5 by 6 in decimal. 5 by 6 equals to 0.8333. Multiply 0.8333 into 2. We will get 1.666. Take integer part. It is 1. This integer part is binary number after binary point. Take 0.666 into 2 equals to 1.333. Since again take integer part, and 0.333 into 2 equals to 0.666. Integer part is 0. Again 0.666 into 2, 1.333. Consider integer part. The pattern is 101 that repeats. So 5 by 6 equals to 0.11010101. Write this in scientific format. 1.101010 into 2 power minus 1. Come to third part, biased exponent. Since 2 power minus 1, true exponent is minus 1. For biased exponents, we will add 127. Biased exponent equals to 127 minus 1 equals to 126. Write 126 in binary in 8 bits equals to 0, 1, 1, 1, 1, 1, 1, 0. Now come to fourth part, assemble. Sign equals to 0 since it is a positive. Exponent equals to 0, 1, 1, 1, 1, 1, 0. For mantissa, we will write up to 23 bits, 10, 10, 10 up to 23 bits. Full binary we will write with SEM order. For group and convert to hexadecimal format, we will come from right to left. Take first four, we will come from left to right. Take first 4 bits, then next 4 bits. Write that 4 bits in decimal. For example, consider first 4 bits 0011, that is 3. Take next 4 bits 111, that is F. Write this up to 8. Then in hexadecimal format 0x 3F 555555.
I'm Srinivas. Now I'm going to solve the second question in the set 2. So let's first see the question and understand it. A processor uses 24-bit instructions with 64 registers and supports 4 addressing modes requiring 2-bit encoding. Standard instructions need 2 registers, 1 addressing mode field, and a 4-bit displacement field. Extended instructions need 1 register, 1 addressing mode field, and an 8-bit immediate field. Special instructions need 3 registers and 1 addressing mode field. Given 32 standard instructions and 16 extended instructions, what is the maximum number of special instructions possible? So the question is telling us to solve the 32-bit instruction encoding problem and to show how many distinct memory type instructions can be supported. Let's first analyze the data that was given in the question. So we have 32-bit instruction and 256 registers. Each register index needs 8 bits because 256 is nothing but 2 power 8. Coming to field requirements according to the format given in the question, there are 4 different types of instructions. There are complex, simple, control, and memory instructions. And the requirements for them, let us see one by one. So, complex instructions, it contains 3 registers. Simple instruction, it contains 2 registers with a 10-bit immediate value. Control instruction, it contains one register with a 12-bit address. And finally, memory instruction, it contains two registers with a 6-bit displacement value. We are told that there are 32 complex instructions, 16 simple instructions, and 64 control instructions. We need to find maximum number of memory instructions. So each opcode combined with all its possible operand values occupies number of distinct 32-bit patterns. That is, since each instruction is of 32 bits and each bit can be represented either by 0 or 1. So total combinations are 2 power 32. That is, the total patterns cannot exceed 2 power 32. Now, let's compute combinations per opcode. And coming to complex, there are 3 registers, that is 256 whole cube, which gives to about 24 per opcode, and we have 32 such opcodes. So totally 32 into 2 power 24 instructions, that is 2 power 29 complex instructions. And coming to simple instructions, there are 2 registers, so 256 whole square into 2 power 10, which says there is 10-bit immediate value. So totally 2 power 26 per opcode, and we have 16 such opcodes. So total instructions are 16 into 2 power 26, which is 2 power 30 simple instructions. Now coming to control instructions, it is 256 into 2 power 12, where 256 represent one register, and which gives 2 power 20 per opcode, and we have 64 such opcodes. So totally 64 into 2 power 20, which is 2 power 26 different types of instructions. And finally, coming to the memory instructions, it is 256 whole square, which represents 2 different registers, and 2 power 6, which gives 2 power 22 per opcode. But the question says us that we need to find total number of memory opcodes. So first, let us encode the total number of instructions that are possible with a 32-bit pattern. Since each pattern is occupied with 0 or 1, so total we have 2 power 32 types of instructions. So encodings consumed by required opcodes. So coming to the complex instruction, they are 32 power 29. Coming to simple instructions, they are 2 power 30. Coming to the control instruction, it is 2 power 26. So total user instructions by these three, that is complex, simple, control, are 2 power 30 plus 2 power 29 plus 2 power 26. And encodings left for memory instructions are nothing but total encodings that are possible with 32 bits subtracted by total user instructions by complex, simple, control, which gives 2 power 32 minus 2 power 30 plus 2 power 29 plus 2 power 26. And encodings per memory opcode, that is 2 power 22, as we have calculated in the above. So maximum memory instructions are 2 power 32 minus 2 power 30 plus 2 power 29 plus 2 power 26 divided by 2 power 22, which gives 2 power 10 minus 2 power 8 minus 2 power 7 minus 2 power 4. So by calculating, we get 624. Finally, the maximum number of distinct memory instructions that can be supported along with the given complex, simple, control instructions are 624. So thank you.
Thank you for your time and attention.
I hope this was informative.
With this, we conclude our presentation. Thank you for listening.